Okey doke, let's go ahead and get started. Does anyone have any questions to begin with?
I have two questions
Okay, Harry, go for it.
from the Module 11 homework.
Let me go
Uh,
ahead and open that up real quick. Okay, there it is, the homework. Okay, which one?
well, I guess the first one I have a question on is 8.
Number 8. A sample of uranium fluoride is found to fuse at the rate of 17.7 milligrams per hour. And under comparable conditions, I2 effuses at a rate of 15.0 milligrams per hour. What is the molar mass of the uranium fluoride and what is its molecular formula? And it says milligrams per hour is not what you want for a rate. So in the lecture, I tell you that the rate is either going to be the volume per time or the moles per time. And the reason for that is wrapped up here in the ideal gas law. So the rate is going to be moles per time, and that's normal. Now, for the ideal gas law, you can see that moles is proportional to volume. So the rate can also be volume per time. However, you'll notice that there's nothing in here that says that the moles is proportional to the mass of the gas. So you can't use the mass of the gas. So when you have 17.7 milligrams of uranium fluoride per hour, you need to turn that into moles of uranium fluoride. And I'm going to say millimoles per hour. Now, also, when you have 15.0 milligrams per hour for, what is it, I2, you want to turn that into millimoles of I2 per hour. And here, I'm going to put a little X here next to the fluorine because we don't know what it is. Okay, so this is what we need to do. We can't do this because we don't know the molar mass of uranium fluoride. And we do need to know that. And if we do know the molar mass of uranium fluoride, we can figure out what its formula is. So what I'm going to do here is I'm going to write a little equation that shows you how to convert this into millimoles of uranium fluoride. So for millimoles of uranium fluoride, we would have 1 millimole of uranium fluoride. And again, I don't know what X is. I don't know how many fluorines there are. And I'm going to call this per, let's see, what variable shall I use? B, milligrams of uranium fluoride. So I can get this value if I know the formula of uranium fluoride, which I don't know. But nonetheless, we can get a formula here that says the rate is going to be 17.7 millimoles of uranium fluoride per B hours. B hours. And that's going to be important for us. That's the rate of the uranium fluoride flow. On the other hand, for iodine, we can do this one. Here, there's going to be for iodine, since iodine has a molar mass of 126.9, this is going to be 126.9 times 2 milligrams of iodine per 1 millimole of iodine. Okay, so usually we say grams per mole for molar mass, but I'm just going to use milligrams per millimole and put m's in front of both of these things. So if I do this, we find out that we get 15 divided by basically 250. So we're going to get a pretty small number here. So we get 0.0591 millimoles of iodine per hour. Okay, so that is the rate of the iodine, and that is the rate of the uranium fluoride. Now, we also know that the rate of the iodine over the rate of the uranium fluoride is equal to the square root of the molar mass of the uranium fluoride over the molar mass of the iodine. Okay, and now that I'm looking back at this, I want to change this. This B is the molar mass of the uranium fluoride. Okay, and when I say that's the molar mass, we've got B milligrams of uranium fluoride per 1 millimole of uranium fluoride, which is the same as B grams of uranium fluoride per 1 mole of uranium fluoride. So B is indeed the molar mass of uranium fluoride. Now I'm going to do one more thing, and that's this. I don't like these millimoles, so I'm going to say that this would be equal to, well, actually, I'll leave it that way. So here, I can now take this formula and these numbers and this idea plus the molar mass of iodine is 126.9 times 2 milligrams of iodine, or excuse me, the molar mass of iodine is 126 point, oh, I guess I did this right, times 2 milligrams of iodine per 1 millimole of iodine. So another thing that I'm doing here is I'm putting everything in terms of millimoles and milligrams instead of moles and grams. So I'm going to use these ideas in this formula. So what I'm going to do here is carefully write these ideas down on a new sheet of paper. So we have B milligrams of uranium fluoride per 1 millimole of uranium fluoride. We've got 126.9 times 2 milligrams of iodine per 1 millimole of iodine. We've got 0.0591 millimoles of iodine per hour. And we've got 17.7 millimoles of uranium fluoride per B hours. So this is everything that I have, and I want to solve for B. So I've got the rate of the flow for the uranium fluoride, or I can put iodine. It doesn't matter which one I put on top. I'm just going to put uranium fluoride on top since I already have that, is equal to the square root of the molar mass of iodine over the molar mass of uranium fluoride. Notice that these switch. The rate, if the rate's on top here on this side, the molar mass is going to be on the bottom. Okay, so let's plug in these values to here. So the rate of the uranium fluoride is going to be B, oh, this is wrong. No, this is right. This is the molar mass of uranium fluoride. I'm going to use this for the flow of uranium fluoride. So I've got 17.7 millimoles of uranium fluoride per B hours, all of that over 0.0591 millimoles of iodine per hour is equal to the molar mass of I2, which is, let me just go ahead and multiply this out. One 126.9 times 2. So I get 253.8 millimoles of I2 per, where is it? There it is, milligrams per 1 millimole. And here I'm going to have B milligrams of uranium fluoride over 1 millimole of uranium fluoride. So right now, it seems like the best thing to do is to try and simplify things as much as we can. So the millimoles cancel, because when you have grams per mole over grams per mole, the moles cancel out. These milligrams also cancel out. And here, these hours cancel out. And here, we don't want to cancel these millimoles out altogether. Actually, I think we can. We can cancel this millimole with that millimole. And this simplifies into 17.7 over B, all over 0.0591 over 1 is equal to the square root of 253.9 over B. Okay, so now I'm going to enlist your help here. Whatever number we get for B, that's the molar mass of the uranium fluoride. I'm going to rewrite this down again. So how do we want to go about solving this? My suggestion would be, let's take care of this side first. So if we take care of this side, we can do 17.7 over B times 1 over 0.0591. You may remember this from algebra. You can take the denominator and invert it and multiply it by the numerator. So here, what we're going to get is 17.7 divided by 0.0591. And this should end up being a pretty large number. So we get 299 over B is equal to the square root of 253.9 over B. So now what are we going to do? We'll square both sides. So I'm going to square this side and I'm going to square this side. Where's my square button on this calculator? Oh, here it is. So for this side, I get 89696 over B squared is equal to 253.9 over B. Now I'm going to take this and do a little cross multiplication. I get 89696 times B is equal to B squared times 253.9. And one of these B's cancels with one of these B's. And we're going to get B is equal to 89696 over 253.9. And so we get 353.3 is the value for B. So that means that we have 353 milligrams of uranium fluoride per 1 millimole of uranium fluoride. or 353 grams of uranium fluoride per 1 mole of uranium fluoride. So this is the molar mass of the uranium fluoride. Now, if we take a look at our periodic table, we'll see that the molar mass of uranium is 238. So that means if I take my 353 and minus 238, let's see what we get. We get 115. So that means that when we take a look at the fluorines, fluorines are 19 grams per mole. I need to find out how many of these are going to make 115. And the way to do that is just say 115 divided by 19. And that's equal to 6. So that means that the formula must be UF6. So this is not your garden variety problem, obviously. And that's why I put it up here, is to try and make you think about all sorts of different things in doing a problem like this. Okay. So if you think about how I did this problem, I did a number of things. First, I realized that the rate of 1 over the rate of 2 is equal to the square root of the molar mass of 2 over the molar mass of 1. And then I realized that the rates must be moles per time or milliliters per time or liters per time, basically volume per time. So that means I took the rates that we were given and I turned them into moles per time. And since I didn't know the molar mass of the uranium fluoride, I had to use a variable for that molar mass. And then for the molar masses, I also had to use variables for the molar mass of uranium fluoride. And then I put it all together and solved for the only thing that I didn't know, which was the molar mass of the uranium fluoride, knowing that that would help me figure out the formula. Okay, now clearly this is a problem that would be very difficult to put on a test, but on the other hand, for homework, this is a great problem for you to look at and spend some time on and think about, well, what are the connections and how can I achieve the result that I want? All right, Harry?
All right.
Pretty tough problem, isn't it?
Yeah, that's for sure.
But I think it's a problem that I just pulled out of the back of the book.
Oh.
I don't know which problem it was, but I looked at it and got, wow, this one has a lot of stuff that would be very interesting to try. Okay, Harry, since you asked one question, it was a really long one. I'm going to give An and Jackie a chance to ask any questions, then we'll come back to you, Harry. Is that all right?
Yeah, no, that's fine. That's fair.
All right, An, Jackie, do you have any questions? Now, the quiz for Module 11 is due today, but the quiz won't have anything as complicated as what we just did, but there might be something about effusion and diffusion on the test. You know, for instance, what effuses faster, CH4 or CF4? And your answer would be, well, CH4, because it's got a smaller molar mass. Smaller things diffuse faster than larger things. You might be also asked, you know, well, which one has got a greater velocity? And the answer is CH4, because it's got a smaller mass. You know, when you look at CH4 versus CF4, you don't even need to make any calculations to know that this is smaller and this is larger. And why is that? Well, because the carbons weigh the same amount, but we know that fluorines weigh much more than single hydrogens, and you got 4 of these and 4 of those. So you don't even need to make calculations for some of these things to figure out that this is going to effuse at a slower rate. And this is going to effuse at a faster rate. Because when you take a look at the rates, if rate 1 is bigger than rate 2, that means that the molar mass of 2 must be greater than the molar mass of 1. So if the molar mass of 2 is greater than the molar mass of 1 and its rate is smaller than the rate of 1, it means that bigger things have a slower rate. Are you guys with me there? So you know that the quizzes are usually things like that that are kind of testing your ability to just understand what these equations mean. Well, you can also expect some sort of a, ideal gas law question on there. And of course, maybe one or two of these. This is supposed to be an N, where you have to decide what things don't change and what things do. Get rid of the things that don't change, and then solve for whatever it is you need to solve for. Is that clear? All right. So since An and Jackie aren't asking any questions, Harry, you're up again.
I just have one more on the homework. It's 9.
Number 9. So did you find the early ones a little bit easier?
Yeah, I found the early ones pretty
Yeah,
easy.
they are supposed to be fairly easy. Okay, number 9. If 12 grams of O2 is required to inflate a balloon to a certain size at 27 degrees Celsius, what mass of O2 is required to inflate it to the same size and pressure at 5 degrees Celsius? Okay, so here again, we're given grams. We're not given the moles, right?
Right.
So this is one of those P1V1 over N1T1 is equal to P2V2 over N2T2. Agreed? Because things are changing.
Right.
Now they say that let's see, what mass is required to inflate it? Okay, I need to draw this. Okay, so we have a balloon of a certain size, and I've got 12.0 grams of O2, and this is 27 degrees Celsius, which I don't want to write down. What I'm going to do is I'm going to go ahead and do this 273.15 plus 27, and I get 300.15 K, because we don't really want to think about things in Celsius. We want to think about things in Kelvin. And here we have a volume is equal to X. We're not given a volume. Fair enough?
Right.
Okay. And then it says, what mass of O2 is required to inflate it to the same size and pressure? Oh, and here, the pressure, I'm going to call it Y. And actually, I'm going to call these V1 and P1, because this is all the first set of conditions. Fair enough?
Yeah.
Now, for the second set of conditions, we have the same size balloon. And since I'm no longer using X here, I'm going to say X grams of O2. And we have 5 degrees Celsius, so that's going to be 278.15 Kelvin. Now, V2 is equal to V1. And I know that because it says inflate it to the same size. And it also says and pressure. So P2 is equal to P1. Fair enough?
Right. Fair enough.
So that means I get to get rid of the P's from this equation and the V's from this equation. So I end up with 1 over N1 T1 is equal to 1 over N2 T2. Now, what is N1? N1 is the moles of O2. But I'm not given moles of O2. I'm giving the grams of O2. Now, how do I get the moles of N2 here? Well, I would say that the moles are going to be 12.0 grams times 1 mole per 32.0 grams. So in this case, I'm going to have, let's see, and I'm going to let this be the molar mass. The molar mass of O2 is 32.0 grams per mole, right?
Right.
Okay, so what I'm doing here to get the moles of N is I'm basically taking 12 grams and I'm dividing by the molar mass of O2. And this is the number I get. So this is all for the first set of conditions. Now, what about the other set of conditions? Well, the moles of O2 here are going to be X grams of O2 divided by 32 grams per mole. So when I clean this up a bit, this is what I get. The moles of O2 is equal to X, the grams cancel, mole per 32. Okay, so here I've got this equation, I've got these temperatures, and I've got these values here. So here you can see I've got stuff all over my sheet of paper. Let's gather it all together into one nice neat place. So 1 over N1 T1 is equal to 1 over N2 T2. T1 is equal to 300.15 K. N1 is equal to 0.375 mole. T2 is equal to 278.15 K. And N2 is equal to X moles over 32. So I'm going to take this equation now, and I see that what I need to do is I need to solve for N2. So I'm going to have N2 T2 is equal to N1 T1. I do the cross multiplication thing. I get N2 is equal to N1 T1 over T2. And so I get N2 is equal to 0.375 moles. Stink my 7 in there. Times 300.15 K over 278.15 K. And I get that N2 is equal to a value that's going to be a little bit bigger than 0.375. And so I get N2 is equal to 0.404, or I'm going to call that 5 mole. Okay. But now I also have this, that X moles over 32 is equal to 0.405 mole. So now I get that X is equal to 32 times 0.405. And I get 12.9. So what was X if we go back to here? X is the grams of oxygen. Okay. So the answer is I need 12.9 grams of oxygen to inflate the balloon to the same size at 5 degrees Celsius. Now we have to ask ourselves, does it make sense that you need more oxygen at a lower temp to get the same size? And the answer is yes, because more grams will mean that you'll have more moles. Colder temperature means you'll have less energy. And so when you combine the less energy plus the more molecules, you should equalize the pressure and get the same volume. Now, how can we check our answer? Well, all we have to do is write out the solution. So here we have V1, we have N1, which is equal to 12.0 grams times 1 mole per 32 grams. We have T1, which is 300.15 K, and we have P1, which is equal to P2. And in this situation, we have V2, which is equal to V1. We have N2, which is going to be 12.0 grams times 1 mole over 32 grams. T2 is 278.15 K, and P2 is equal to P1. So when we put this all together, we get 1 over N1 T1 is equal to 1 over N2 T2. And all we have to do is plug these numbers in here and see what we get. So I'm going to plug in 1 over 12 over 32 times 300.15. And here I'm going to do 12.9 over 32 times 278.15 and see if we get this side equaling that side. So 12 times 300.15 divided by 32. So I get 1 over 112.55. And here I get 112.12. And you can see that these are essentially the same amount. So it works out. So any questions there, Harry?
Nope. That helped me out.
So this is like the previous problem where you have to do a little finagling to figure out what's going on. These are the kind of problems in the chapter that I like because they're more challenging. And when you butt your head against these challenging problems, you really start to learn the intricacies of the different formulas and things that you're looking at and the ideas behind them. So here we're forced to recognize that we're given the problem in grams. We need the masses. Now, is there probably another way to do this? Absolutely. There is probably another way to do it. For instance, we know that density is PM over RT, right? And maybe we could have used this formula and this formula to figure out what's going on. Although I kind of doubt it. Okay. We're going to pause the recording so we don't have to listen to someone leave a message on my phone. I think the reason I have the landline is in case somehow the cell phones go out, I'll still be able to make calls. Okay. Is that it? Okay, so you should notice, or maybe you haven't, but I do want you to take a look at Module 12. I have posted the lectures. And I will be posting the homework later today. And then after I post the homework, hopefully I can get to the grading of the exams. But I want to talk about Module 12. Module 12 is about organic chemistry. And what I think is more important about organic chemistry is a little bit different than what the book has. So for the organic chemistry section, I agree with some of what the book has. I've separated it into basically 4 sections. One section is called Why Carbon. Another section is called Organic Chemistry. Another section is called Hydrocarbons. And then another section is called Reactions. So rather than duplicate what's in the lectures, I will tell you that in this particular section, Why Carbon, we talk about the reason why there are so many different organic compounds. So what is an organic compound? Well, naturally, an organic compound is something that is made by some organism that is grown organically, that is without pesticides. So when they make their compounds, those compounds are considered to be organic. Now, do you feel like you're getting a little taller? On? Harry, Jackie, you feel like you're getting a little taller? That's a yes or no question. So organic compounds are made by organic organisms. You feel like you're getting a little taller? You should feel like you're getting a little taller because I'm pulling your leg. Organic compounds are not compounds made by organic organisms. Organic compounds simply means they contain carbon. And often it means that it's made by organisms. So CO2 is definitely an organic compound. So this is different than the idea of organic that the layman has, where organic from the layman means that it's anything grown without, grown only with natural pesticides. So if there's some sort of pesticide you can use for your crop that is natural, that's okay, but you can't use man-made pesticides. So organic means something totally different for chemists than it does for the farmer. Organic means it contains carbon. And so there's a study of organic chemistry, which is the study of carbon compounds. Okay, now why do we study organic chemistry? And really the reason we study organic chemistry is for the biology in it. It turns out that for biological organisms, you need to have carbon-containing compounds. And if you can understand how those chemicals react, you will understand better how organisms behave. If we did not have organic chemistry, we would not have vaccines being prepared for COVID-19. Okay, so organic chemistry allows us to prepare those vaccines because we understand the chemistry behind how the virus infects someone and possibly how to combat that. Okay, so organic chemistry is the study of carbon-containing compounds. Now, in addition to wanting to know how carbon-containing compounds react, it's important to know that there are something like 20 million different organic compounds that have been cataloged. 20 million. Now, when you compare organic chemistry to something called inorganic chemistry, that would be the chemistry of compounds that do not contain carbon. There are only about 500,000 inorganic compounds. So let's think about that. 20 plus million organic compounds, 500,000 inorganic. So it turns out that most of the chemistry we're interested in is going to deal with organic chemistry, not inorganic chemistry. So let's talk about the diversity or the reason for 20 million organic compounds. So O for organic. Well, there's two basic reasons why there's so many organic compounds. One, there's 20 million species making them. That's a count I heard sometime before that there's 20 million different species in the world. The number may be going down as extinction events occur, but there's a whole lot of different species. And this is really interesting. If there's 20 million different species, and we know that the species should be slightly different than other things, why are there only 20 million organic compounds? And the answer is that a lot of the organic compounds in any species is the same as the organic compound in another species. All vertebrates use ATP. That's an organic compound. And they use ATP to make ADP. All vertebrates have those two same organic compounds. So a lot of the organic compounds that are used metabolically are identical in the different organisms. So that's why we only have about 20 million compounds, even though there's 20 million species. That is to say, each species is not made up of a list of organic compounds that is different from every other species. The only thing that makes the species different is the DNA. Okay. Another reason why there's so many different organic compounds is because of the diversity of carbon. Now, why is carbon so diverse? Well, I'm going to let you watch the lecture because I give you a list of 10 different things for why carbon is so diverse. And rather than just say those things again, watch the lecture. On exams, I almost always put a question down about, list the different ways that is diverse. One thing I do want to say about the diversity of carbon is the science fiction people always talk about, well, there's probably silicon based life form out there. And the reason they say that is because on the periodic table, here's carbon and here's silicon. And we know that elements in the same group have similar chemical properties. Well, if carbon can be the basis of life one place, then silicon should be able to be the basis of life another place. And to that I say poppycock. It's simply not possible. And the reason is for the diversity of carbon compounds. Silicon does not have that same diversity. And when you have organisms where you're basing it on one element, you want to have that element be diverse so you can have diverse organisms. So silicon simply doesn't work. I will give you one example where carbon is much better than silicon. Carbon compounds, some are gases at room temp, some are liquids at room temp, and some are solids at room temp. So that means that when you have these living organisms, you can have some compounds that are gases at room temp, some that are liquid, they're squishy, they can move around, and some that are solids at room temp. And that's kind of important. I certainly like the fact that I can eat a solid diet instead of a liquid diet all the time. That's pleasing to me. When you talk about silicon compounds, what are they usually made out of? Well, some of them are gases, some are liquids, but most of them are solids. A very common silicon compound is silicon oxide. Now, a very common carbon compound is CO2. This CO2 for organisms is a metabolic waste. We take carbon compounds, we oxidize them and turn them into CO2, and this is a waste product. How do we get rid of that waste product? We breathe it out. And CO2 is odorless. It's a gas at room temp. So we make it continuously. So it's nice that when we breathe, we can continuously expel it. So you probably have never thought about that when you breathe out, you're breathing out waste, but you are metabolic waste. Okay. Now, what if you used silicon compounds as your source of energy? You would oxidize them and turn them into silicon oxides. Silicon oxides are solids at room temp. So imagine if you were this organism and you had to expel silicon oxide all the time. That would mean if you had a butt, you would be leaking sand out of it continuously because you're metabolizing silicon. So think about how society would be if instead of breathing out CO2 gas, which is odorless, we're pooping out sand from our butt. And sand is abrasive. I would hate to be pooping out sand all the time. But on the other hand, it would probably mean that our butt would be like a rock. And so even though it's a rock, I guess rocks do wear out other rocks. So it would just be an interesting society. I mean, can you imagine what pants would look like if you were pooping out sand all the time? Would they have pockets that would catch it, or would you just put a little hole there? I don't know. But at any rate, it disturbs me enough to say that I really don't think silicon-based life forms are going to occur. Now, what if we increase the temperature? Well, then this stuff would be a gas, but it'd be a really high temperature. And so I hope to heck that we never run into silicon-based life forms, because if we do, they're going to want things to be a lot hotter than we want them to be. And if we're in their environment, we would be incinerated. And if they were in our environment, they would freeze and look like a rock. So I don't know, but when you go outside and you pick up a rock, that may be a frozen silicon-based life form. Guys feel like you're getting a little taller? That's a yes or no question. No answer? Because I'm pulling your leg. Don't go outside and pick up a rock and think that you can talk to it. Capiche? That's another yes or no question. I think I lost Harry. Okay. Let's talk about two major topics in organic chemistry. Now, we already know that organic chemistry is the study of carbon-containing compounds. Two big topics in organic chemistry are functional groups and representing compounds. So I want to talk about representing compounds so you understand clearly the different ways of representing organic compounds, and then we'll talk about functional groups, okay? So let's look at compounds and how we would represent them. There's one thing that's called the molecular formula. And that's the list of elements and how many. Then there is something that's called a Lewis structure. This shows atoms, bonds, and lone pairs. There's also something called a structural formula. A structural formula shows atoms and bonds, but the lone pairs are implied, they're not shown. There's something called a condensed formula, which is a list of the atoms with the connections implied. And there's a little caveat there. We do show some connections. So here, I'm going to cross out the word bond, connections. I'm going to put the bonds. The single bonds are implied, and we show double and triple bonds. And here, we don't show the lone pairs. So you kind of do the condensed from the structural formula. And then there's something called the line drawing. And here, carbons and hydrogens bonded to carbon are implied. So these are the different ways of representing compounds. And we're actually going to start here. And from here, we're going to get the Lewis structure, the structural formula, the condensed structure, and then the molecular formula. So let me show you a line drawing. This is the line drawing of something called aspirin. Now, this is something you may not know, but aspirin actually has 3 syllables. It's not aspirin, it's aspirin. So this is aspirin, and this is an organic compound. It contains carbon, and you don't see any carbon atoms here. So let me show you how to turn this into a Lewis structure. The first thing we have to know about this is that lines are bonds. So can you see this line right here that I'm pointing to? That is a bond. Can you see these 2 lines that I'm pointing to? That's 2 bonds. Can you see this line here? That's a bond. Can you see these 2 lines? That's a double bond. Well, what looks like a double bond. Okay, so my first question to you is, do you understand that every line is a bond? Yes or no? Every line is a bond. How about you, Harry? Are you good on this? Every line is a bond. All right. Secondly, if you see an atom at the end of the bond goes to that atom. But if you don't see an atom at the end of the bond, it's a carbon atom. So here, the bonds are between carbon atoms unless otherwise specified. So how do you specify that the line does not end in carbon? You put the element there. Okay, so we can now take this guy and we can put in carbon atoms. So you see this OH, that's that OH. You see this line here? That's a bond that ends in carbon. So that's a carbon atom right there. This carbon atom is also double bonded to oxygen. And this carbon atom is also bonded to that right there, which is another carbon atom. How do I know that's not carbon? How do I know that's carbon, not oxygen or nitrogen or fluorine? And the answer is, if it were nitrogen, it would say N there. If it were oxygen, there'd be an O there. The fact that there isn't those symbols there means it's a carbon. So if the atom is not specified, it's carbon. Okay, so now we've got this double bond, if you will, that goes to a carbon. And a single bond that goes to a, who wants to guess? What does this bond go to here?
Is it another carbon?
It's another carbon. Do you see how easy the rules are? And then we have a double bond. What does that go to? Someone else other than Harry.
Oh, it's carbon.
Carbon. And then the single bond goes to someone else other than Harry or An.
A carbon.
A carbon. You guys like this game? This game looks pretty simple, doesn't it? So we have all these carbons. Look at this bond. What does it go to? Who wants to guess this one? So what does this bond go to? From carbon to what? Oxygen. How do you know it's oxygen?
Because it's specified.
Because it's specified. Now this one's weird. You see this line here? It goes from this carbon here that I've drawn to what? What atom is right there that I'm pointing at?
Is it carbon?
It's carbon. How do you know it's carbon? Because it doesn't say anything else. Okay, so that's how you start to fill in line drawings. Third, every carbon has 4 bonds. And to make this so, you add single bonded hydrogens to carbons to get 4 bonds. So take a look at this carbon here that I'm pointing at. How many bonds do you see to that carbon? Well, 1, 2, 3, 4. So that carbon has 4 bonds. We don't add hydrogen to it. Let's look at this carbon. How many bonds do we see to it? Get an answer in your head. And the answer should be 4. 1, 2, 3, 4. So nothing to do there. Now I'm going to point at this carbon. How many bonds do you see? Get an answer in your head. And the answer is you see 3 bonds. So what do? We add a hydrogen. And now it has 4 bonds. So are you guys beginning to understand the game? How many bonds do you see to that carbon? 3. So what do we add to that? A hydrogen. How many bonds do you see to that carbon? 3. So we add a hydrogen. So answer this question for me. How many hydrogens do we add to this carbon? Someone unmute themselves and give me an answer. How many hydrogens do we add to this one?
1 hydrogen.
Correct. Okay, someone other than Jackie, how many hydrogens do we add to this carbon that I'm pointing at?
You wouldn't add any hydrogens. So it's the same
0,
4
that's
bonds.
correct. And the same for this one also. So that leaves you on, how many hydrogens do I put on this carbon?
3.
Correct. So here's 1, here's 2, and here's 3. Now we have to do a little bit more to this. We want to add lone pairs. Now, where do we add lone pairs to? We add lone pairs to atoms so that you can get an octet. So do you see why I added 2 lone pairs to that oxygen? So we can have 8 electrons there. Now, this thing we want to fix, and so here's what I'm going to do to fix it. I'm going to erase it. And this is something I probably should have done at the get-go. Instead of OH, I should have done this because we know hydrogen makes single bonds, right? So I draw that, and I have 2 lone pairs on that oxygen. And I need to use my whiteout to make sure that you don't think this is a lone pair right here. There we go. So there we go. This is the Lewis structure. Capiche? So what I'm going to do is I'm not going to draw the structural formula. Oh, what the heck? I might as well. So here's the structural formula. So this is the Lewis. This is the structural formula. So what is the big difference between these two? The answer is the structural formula does not show lone pairs, they are implied. Okay, so this was a kind of tough one to do. Let's do something more, something easier, but it'll also be tough. I want you to draw the Lewis structure for this guy. When you're done, give me a thumbs up and we'll check and see if you're correct. And I almost always put one of these on a test, on an exam. I give you a line drawing and I say, okay, give me the Lewis, the structural, the condensed, and the molecular. Give me the thumbs up when you have it done. Okay, I hope you have that to begin with. And then you decided that you wanted to put 3 hydrogens on this guy. And you decided that you wanted to put 3 hydrogens on this guy. And then lastly, you wanted to put 2 lone pairs on oxygen so it has an octet. So how did we do? Thumbs up or thumbs down? Well, give me a thumbs up if you felt like you did okay. Now I want you to draw the structural formula. Give me a thumbs up when you're done with the structural. Okay, so you should have something that looks like this. and the lone pairs are not drawn. Now, next, we're going to do the condensed, but I'm going to let you figure out what the condensed looks like here based on this guy here. So this is a line drawing. And the Lewis structure is going to look like this. The structural formula is the same. Why is the structural formula the same? No lone pairs. Now the condensed formula, you start with a branching atom. So that's an atom that is bonded to two or more other atoms. This hydrogen is not branching, it's only bonded to one other atom. So we're going to start with this guy. And then we're going to put all of the terminal atoms that are bonded to it. And then we do the next branching atom, which is this carbon, and then its terminals. And then the next branching atom and its terminals. So it's like a branch, terminal, branch, terminal, branch, terminal. That's how you write the condensed formula. I call it the typewriter formula because if you're writing a book 100 years ago and they only have typewriters, this is something you can achieve on a typewriter very easily. This is something very hard to do. So condensed formulas are the typewriter formula. Now, for those of you who are wondering, what's a typewriter? Google it, watch a video, and you'll see. Okay, so if this is the condensed formula for this molecule, write the condensed formula for this molecule. When you're done, give me a thumbs up. Okay, hopefully you have this. You'll notice that in the case of the second one, there are no terminals, so you don't put anything afterwards. Okay, now there's the molecular formula, which means you just count atoms. How many carbons? 2. How many hydrogens? 6. How many oxygens? 1. And there's the molecular formula. Okay, are you ready for another try? A different molecule. And I want you to do all of these for this new molecule. Here we go. When you're done with all of them, give me a thumbs up. Here's the molecule. Okay, this is what you should have. Some people forget the bond here between the oxygen and the hydrogen. Don't forget it. You need to show all bonds. And here are the lone pairs. Here's the structural. Whoops, that's a carbon. Let me use my whiteout to correct that. Here's the structural. There's the condensed. and there's the molecular. Now I'm going to give you another example, which is a little difficult. This is a molecule called aniline. Let me show you how to turn this into a Lewis structure. Put the double bonds in. Okay, so you can probably get the Lewis structure. The tough one here is that nitrogen needs to have one lone pair on it so it has an octet. The structural formula is going to look the same, but without the lone pairs. Now, can you see, looking at this molecule, based on our interpretation, that there are 6 carbons? Can you see that? So here, looking at this, based on our interpretation, can you see that there's a lone pair on nitrogen so that it can have an octet? So just like carbons are implied here, lone pairs are implied in structural formulas. Now, the condensed structure, for something like this, you do this. These 6 carbons in the ring and these 5 hydrogens, the condensed formula for that is C6H5. And there's the condensed formula. So I wanted to let you know that because this one is a little difficult. And then the molecular formula is C6H7N. This is not a molecular formula. It's a condensed. And sometimes people forget to just make a list when they get to the molecular. So I'm going to leave you with one more problem and then we'll call it quits here. I want you to take the following drawing and I want you to write out the Lewis, the structural, the condensed, and the molecular formula. When you're done, give me a thumbs up and we'll call it quits on this. We'll finish it all up on Wednesday. Are you closing in on it, Harry? Okay, so let's look at the condensed. C6H5O CH3. Now you can see that when you're looking at these, what's probably the easiest one to get the molecular formula? And it's this guy here. 6 carbons plus 1, 7 carbons, 5 hydrogens plus 3, 8 hydrogens, 1 oxygen. Any questions there? So let me ask you, if you are writing a book and you want to show complex molecules, and by the way, these are not complex, they're very simple. Would you rather do this or this when you're trying to indicate to people what they're looking at? And the answer is this. Okay, so this is a way of communicating what the molecule is made out of in a very deliberate way that's very efficient. And what's even more, and I didn't show you this and I'm not requiring it, but I'm going to show you now, is that this is also a 3-dimensional drawing to me. And I'll show you what I mean. So here, I'm going to put a little oxygen there. This is a 3-dimensional drawing to me. So you can see how it's a COC. And if we put the hydrogens there, I know there's 2 more hydrogens here. And you can see that these carbons with 4 things attached to it are tetrahedral. This one's also tetrahedral. This oxygen with 2 things attached to it is bent. 4 pairs and 2 bonds, it's bent. This is the molecule drawn in 3 dimensions. So when I look at this guy, I actually see the 3-dimensionality. Furthermore, these rotate freely around the single bond. So not only do I see the 3-dimensionality of this, I see how it's behaving like a video. So this thing is running around in space and these bonds are spinning. This thing is like a propeller, 2 propellers on the end. It's just a fantastic world. Now, you're not required to do this. This is a little much, but you will be required to be given a line, if given a line drawing, to be able to draw the Lewis, draw the structural formula, draw the condensed, and write out the molecular formula. Is there anything, well, is that clear? Okay, very good. I will put a little practice, well, I'm going to put some problems like this on your homework where you can practice them. And I think that you'll find that these things are just kind of fun to do. They're not difficult whatsoever. And now if you go online and you look up some medication that someone happens to be taking, like acetaminophen or naproxen, and they give you some structure, you're going to be able to say, oh, I can figure out what the formula is of that compound. Capiche? All right, folks, thanks for listening. I will try to post this Q&A as soon as I can. It usually takes about an hour for the video to process. And the problem with that is that in that hour, I usually start doing something else and I forget about it. But I'll try to remember to post this one as soon as possible so that you can look at it in the Q&A for Module 12. You want to tune in Wednesday because we're going to cover the rest of Module 12, and you're going to have a quiz on Module 12 on Friday. As far as your last exam, that'll be Tuesday of next week, and your final will be Wednesday of next week. The final is a complete multiple choice exam, 55 questions. Each question is worth 2 points. So you can get 110 points on the final exam, but it's graded out of 100 points. So you could get 110 out of 100, and that'd be extra credit. And remember, the final is worth 20% of your overall grade. The last exam will cover the last 3 chapters, and I'm trying to give you a great idea of what to expect on that exam that you're going to have next Tuesday. For instance, if you look at the gases, what are the big things for the gases? Well, you've got the ideal gas law. You've got the P1V1 over N1T1 is equal to P2V2 over N2T2 stuff. You've got the kinetic molecular theory. You've got effusion. You've got density. And these are probably the big topics that are involved in the gases. And if you look at this chapter here, you saw that I already outlined this last chapter for carbon. You got the Y carbon, you got the organic chemistry. And for the organic chemistry, we have the stuff that we covered today is drawing these things. On Wednesday, we'll cover functional groups. And also we have hydrocarbons and reactions. And the reactions are going to be fairly straightforward. I'm only going to have you memorize 2 types of reactions. The hydrocarbons, we're going to look at ways of, we're going to be looking at basically isomers and naming them. So this is what we're going to cover on Wednesday. We'll also cover a little bit of this on Friday. Your quiz you can take later in the day on Friday. What was the previous chapter? The previous chapter was valence bond theory and molecular orbital theory. So what are the big things here? Hybridization. Pi bonds, sigma bonds, principles of MO, let's see, the energy diagrams, electron configuration, sigma bonds and pi bonds, magnetism, and the electron configuration. So these are the big things that you will see on your chapter. This list may not be complete, but these are the big ideas from those 3 chapters that you want to be able to be pretty fluent with. Okay, and you know the effusion one is that rate 1 over rate 2 is equal to the molar mass of 2 over the molar mass of 1. That's the effusion part. So that'll be on your last exam. And of course, all of these things plus more will be on your final exam. And for those of you who are kind of worried about the final exam, you have to understand, here's how I look at the final exam. There's going to be 55 questions and you get 2 hours to do that. 2 hours is 120 minutes. So 55 into 120 means you'll have about 2 minutes to do each question. So will I be able to write down complex, solve this with a lot of calculations problems on the final exam? Will I be able to put 55 of those on the final exam? And the answer is absolutely not. It's impossible for you to accomplish that. But I might have questions like this. How much does 0.5 moles of magnesium weigh? And I could have answers like A, B, C, D, E. I could have 24.31 grams, 24.31 ounces, 12.16 grams, 0.5 grams, and so forth. I could have choices like this. And how do you do a problem like this? And the answer is use your wits. You don't need a calculation. You could certainly do this 0.5 moles times 24.31 grams per 1 mole. Or you could just say to yourself, well, gee whiz, if 1 mole weighs 24 grams, half a mole weighs 12 grams. I choose C and you move on. So I put a lot of those types of questions on the exam, the final exam, where, yeah, you can waste your time and do a calculation, or you can use what you know and make sense out of it. So usually on my final exams of 55 questions, people finish in about an hour and 15 minutes to an hour and a half. Some people that are really careful and they double check their answers, they'll use the full 2 hours. But even they finish the bulk of their exam in about an hour and 15 minutes to an hour and a half. So with that final exam, with 55 questions and 2 minutes per question, I would expect this question to take you about 15 seconds. And therefore you save 45 seconds for another problem. Now, on the final exam, will I put some problems that will require calculations? Absolutely. For instance, what is one of the biggest problems we've had to do in this whole semester that has to do with calculations? And the answer is stoichiometry. So there'll probably be a stoichiometry problem where you'll have to do some calculations. So don't be afraid of the final exam. Look at it as an opportunity to hone your skills and apply them and to make sense out of problems. Is that clear? Okay. And people actually, on the final exam, they tend to do as well on the final exam as they've done on the rest of the semester. Some people actually do better on the final exam because you don't have to show your work. So Tony can't ding you for not showing your work. All right. Thank you for listening, folks. I hope to catch you on Wednesday, and turn on your mics and say hi, say goodbye to everybody.
Bye, everyone.
All right. We'll see you Wednesday. I hope to see you Wednesday. Bye-bye.
Bye.